Alright, so in the previous video, we went through what is a standing wave, but quite often in NCEA, you'll be asked, how is a standing wave formed? Alright, so one way a standing wave can be formed is in a piece of string. In the next video, I'll be going through the different types of mediums that a standing wave can form. But for this video, to describe how a standing wave is formed, I will be using a string. So in this video, I'll be going through a step-by-step explanation on how a standing wave is formed. And in that explanation, we'll begin to see the difference between progressive waves and standing waves. And the key difference between standing waves and progressive waves is the idea that standing waves have fixed points of nodes and antinodes. Alright, so I'm going to have a string, right? So it will be at two ends, so these are two fixed ends. Alright, so I'm going to have a string now in between points A and point B, and this is going to be a fixed length, okay? So this is when no wave is formed in the string. So for this explanation, I'm going to draw one form of a standing wave that can form in the string. There are multiple forms, but for this one, I'm going to draw the second harmonic, and the second harmonic will look something like this. Oh, let's see if I can do that better. There we go, that's better. So that's the oncoming wave, and we can also draw the reflective wave like so. All right, so remember, for standing waves to form, we need two sources, meaning two waves, okay? And those waves have to interfere, like I said in the previous video. And as you can see, these two waves are interfering right now. So what we can notice straight away is that there are regions of zero displacement. So that would be on this side and on this side right here. This happens because these are fixed ends, right? So the ends are fixed. So fixed ends, like I said previously. And just for clarity, our N stands for nodes, all right? And you'll also notice that there is a node in the middle. So those three parts of the string don't displace at all. They stay at zero displacement, okay? And you can see that in the simulation in the previous video. And so along with those three nodes, we can see we have two antinodes, right in the middle here and right in the middle here, okay? So again, A is antinodes. And if you remember back to the previous video, when we have a standing wave, we don't observe the energy being transferred in either directions, all right? So we don't observe that. What we do observe is if we take this region right here, we observe that this region comes up and down, like so. And in the exact same way, we see this region of the wave also oscillating up and down like a trampoline in phase, all right? And it's important to note, let's call this region region A, and let's call this region B, okay? So I should make that also lowercase. It's important to note that region B is 180 degrees phase shifted compared to section A, okay? So 180 degrees phase shifted, what that means is that at section B, if we have a trough, we will have a crest on section A. So now starting off with our explanation, we can say point number one, the wave progresses along the string and is reflected at the ends. So let's say the wave starts at point A, it travels along, and then it reflects at point B and goes through a 180 degrees phase change and progresses down this way, and it continues on and on and on. And you can see that's what I've tried to depict with these white and orange lines, okay? You can see how the orange line is 180 degrees out of phase with the white line, okay? And so that brings us to our second point, where the reflective wave is 180 degrees phase shifted from the oncoming wave. The third part to this explanation is that the oncoming wave and the reflective wave interfere with each other, right? And due to this is the reason why we get our regions of antinodes and nodes. Okay, if we remember to our previous video, when we have a situation where we have a crest and a trough meeting together, we get destructive interference and therefore no wave is formed, right? However, if we get a situation where we have two crests or two troughs meeting together, right? So if we have two troughs meeting together, that is the exact same thing as this situation right here, okay? So if we either have two crests or two troughs meeting together, we get constructive interference, which results in an even larger wave, okay? And so from our section 3, we can say that regions of constructive interference result in antinodes, and regions of destructive interference result in a node. So this point right here deals with this central node. However, the nodes at the ends must be nodes due to the boundary conditions. And in this case, the boundary conditions are fixed ends. So that can be our fourth point, right? Fourth point, due to boundary conditions. And our boundary conditions in this case is fixed at both ends. This means we must have nodes at both ends, all right? Now, this is important because there are cases where we will have antinodes at the ends, right? You will see a situation where we have an open-ended pipe, and in the open-ended pipe, you'll find that we have an antinode at the end and a node at the other end. So in that case, we would say due to the boundary conditions where we have a closed end and an open end, this means we must have an antinode on one side and a node on the other, right? So this paragraph changes depending on which standing wave you're talking about. And that really just goes for all these points, right? These aren't just fixed points that you can just regurgitate in the exam and get an excellence or get a merit or whatever. I would encourage you to really try and think about what each point is actually trying to say, understand the underlying physics, and so that way you can actually change the explanation based on the question that is proposed in the exam. Now, the last thing that we will need to say, and this is the crucial bit, so I'll spend more time on this after I explain this point. Due to the speed of the wave, and also length of the string, only specific wavelengths will fit to create standing waves, right? And so the key idea is that only specific wavelengths will fit, okay? So what does that mean, right? So let's say that we have a case similar to this case above, where we have 2 points, right? A string in between 2 points, again, A and B, whatever you want to call it. And let's say this length is 2 meters long, okay? And I'll draw a couple more to emphasize the point. You'll see what I mean, okay? And these are, again, all 2 meters. So the one that we've drawn already, like I said previously, if you remember, I said that this is the second harmonic, all right? So we can draw that here, and we can see that this is one full wavelength, right? And just like above, we can draw our nodes and antinodes, so we know that this is a node, this is a node, this is a node, and this is an antinode and antinode over here. So as we can see here, the relationship between the length and the wavelength is that the length is equal to the wavelength. Because like I said before, we fit one full wavelength in between this 2 meter length. And so the wavelength has to be equal to the length of the string. Okay? If we go back a bit, we can see that there is actually another standing wave that can form as well. And that would be when we have 2 nodes on either side and an antinode in the middle. So an antinode in the middle and 2 nodes on either side. And as you can see, this is actually half a wavelength. So wavelength over 2, or 1 over 2 lambda, like that. Right? And you can see that this shape resembles this half of this wave. And so, like I said, we have half a wavelength. Now, I should really make this bottom one orange because that would emphasize the point, all right, like so. And you can see that this is a standing wave because we can imagine that this wave will just oscillate up and down like so. And so in this case, the length is equal to half the wavelength, all right? And so you can see that no other wavelength in between would fit, right? If we imagine a slightly longer wavelength, let's use this color right here. So a slightly longer wavelength would go up like this and come down, and it won't quite have a node at this end because we need a node at this end. There is no other wavelength in between these two that can fit, all right? And so we would call this the fundamental frequency, right? Fundamental frequency. And this is also called the first harmonic. Okay, so you will see both in exams. And this right here, if we were to move this up here, this is called the second harmonic. And you can, if you want, predict what this third harmonic will look like. So this right here is the third harmonic, okay? And if you want, you can predict what this is going to look like, but I will draw it out for you. It'll look like something like this-ish, okay? And as you can see here, we have a node over here, a node over here, node of, that should be lower down, but whatever, a node over here, and antinode, antinode, and antinode. And as you can see, we have one wavelength over here, and then another half wavelength over here. So we have 1.5 wavelengths in this length, and so therefore the length is equal to 1.5 or 3 over 2 lambda, like so. So what we can say from this is that if we have a case where we have nodes on both ends, right? So boundary condition, as we said before, is when we have fixed ends and therefore nodes at boundaries. So our boundary conditions is that we have fixed ends and therefore we have nodes on both ends. And in this case, only whole number of half wavelengths will fit. So only whole number of half wavelengths will fit and form a standing wave. And so the only caveat here is that this is also a whole number of half wavelengths because we can rewrite this as 2 over 2 lambda, right? So that means we can fit 2 half wavelengths in the length and therefore 2 halves mean a whole, right? And so this will continue on to the 4th harmonic, the 5th, 6th, 7th, right? It will just keep going. And you can imagine that in the 4th harmonic, we would have 4 over 2 lambda, which will be 2 lambda. And then in the 5th, we would have 5 over 2 lambda, etc., right? In my recollection, we don't ever really go past the 5th harmonic. And usually when we do go past the 5th harmonic, that's when we have a case where we have an open and closed-ended pipe. I'll go into more of that in the next video. All right, so yeah, in the next video, I'll be going on to how this applies to different mediums that standing waves can be formed into, all right? But the key idea of standing waves is that the wave progresses along the medium, in this case is a string, and is reflected at the ends, all right? Then when it's reflected, it goes through a 180 degrees phase change, and then that reflected wave interferes with the oncoming wave, okay? And this results in constructive interference and antinodes, and destructive interference and nodes. Because of the length of the medium, and also the speed of the wave, only specific wavelengths can form, all right? So that would be it for this video, and we can move on to part 3.